Okay, and we're back. So what we're going to assume that P is isolated. So if P is isolated in lambda, then that means if P is in lambda, then there's some interval around P that's got no other points in lambda in there. Everybody else here is not in lambda. Well, if everybody else is in there in lambda, then they must leave, right? If every point closer and closer to lambda, to P, if they take more and more iterates, like maybe this one will leave when you iterate the function 20 times, and maybe this one 100 times, and maybe that one 1,000 times, and it takes more and more iterates for those guys to get away, for them to escape, then that means each one of them is going to be in a different a sub k, because they're going to take longer and longer to escape. And so that means there would be a sequence of a sub k's. I mean, that would be some a sub k, that would be another a, and that would be another a, and that would be another a. And so if successively closer points take longer and longer to escape, then that means there's going to be a whole sequence of a sub k's getting closer and closer to our point P. But if there's a whole sequence of taking more and more iterates, and so that means more and more values for this k, then remember that we started this conversation by saying that the endpoints of all the a's are in lambda. So that means there's a sequence of points in lambda that are getting closer and closer to P. So that's a contradiction. That means P is not isolated, because there's always closer and closer points. So that was case one, and that is that everybody there takes longer. The closer you get to P, the longer and longer it takes to escape. Well, if that process stops sometime eventually, then that means that the closer you get to P, then it doesn't take more and more iterates to escape. Then that means that there is going to be some magic number of iterates that once you iterate that many times, all the folks nearby go out. Everybody in the neighborhood of P, except of course P itself, goes out with some particular iterative f, one particular count for like that a sub k, one particular choice for k is enough, and everybody in the neighborhood is gone at that point. And if P stays in but everybody in the neighborhood goes out, then that means ultimately what's going to happen is it's going to be that there is some constant, there's some number of iterations, so that if everybody is ultimately goes outside but P stays in, then if you iterate some more, then it's going to end up going to 0, and the other guys aren't. So you'd have some place so that the nth iterate applied to P gets you at 0, but the nth iterate for everybody else nearby in this interval, everybody else ends up being negative, because that's what it means to go outside, right? That if it's up here, then you're over here, then you're down there, then you're negative. So your x value is negative ultimately. And so that means there's some point where the P stays in, but everybody else has gone over there negative. So that means you've got something to which we can apply some sort of calculus stuff there, right? I mean, there's this interval, and P's in there, and P with this particular function applied to it gives you 0, but everybody else is negative. Then that's like whatever that nth iterate function is, there's a max there at P, right? So if there's a local max at P, then that means that nth iterate function, you take the derivative and you plug in P, and what you get is 0. Because there must be a max there for this function. If there's a max, the local max, then the derivative is 0. But now, that's a derivative of an nth iterate again, and so we've got our chain rule buddy, right? That nth derivative, the nth iterate, you take its derivative, that's f prime with one fewer in there, and then you take the derivative of that, and it's f prime with one fewer in there, and then you keep going and you have f prime with f of P, and then finally you have f prime with P plugged in, right? But we just said that one of those is 0. And so that means for somebody in there, one of those is exactly 0. So there should be some place where f prime, where the nth iterate of P, so one of these guys in here, one of these, has to be equal to 0. And so that's for some I that's less than n, because we haven't gotten up to the n thing, right? These are all the smaller ones. That's n minus 1, n minus 2, n minus 3, as you go down there. So that function inside there, that's just the original function f, right? And so if its derivative is 0, threw the arrow in the wrong place. That's the derivative, right? These are just different points. There's p and f of p and f of that and f of that and f of that. These are just a bunch of points. And because p is in lambda, all those guys stay inside lambda all forever. So that's a point, and that's a point, and that's a point, and that's a point. All those guys are points in lambda. And so now what we've got is this is the good old original function f. So f prime being 0, well, that only happens at one place. That's at, darn, that's at x equals a half, right? Actually, it's taller than that, right? The only place the original function derivative is 0, it's just a parabola. So that only happens when the x equals a half. So that means there's somebody here. So the ith iter of p has to equal a half, because that's the only place where f prime is 0, where that's equal to a half. But then if that means the ith iterative p is a half, then that means when you iterate again, then you're outside. And so that means p ends up going to minus infinity